So let's go ahead and we'll look at integration. Now the question we want to answer is, if we were to integrate a function in time, what would happen to that function in frequency? So what we can do is, in order to integrate a function, we can convolve the function with the unit step. So that's f of t convolved with u of t. Now let's have a wee look at this graphically, and we'll see if we can work out why this is the case. So let's take a function u of t. Now we know that in order to convolve this, we've got to take one of these functions and we've got to introduce a dummy variable. We've got to flip it in the y-axis, so it's a mirror symmetry in the y-axis. So let's do that with the u of t. So rather than u of t, we'll call it u of tau. This axis becomes tau. We then flip this on the axis and this becomes u of t minus tau. So we're adding on little increments here and it moves along this tau axis. So this heads off to infinity in the negative direction here. So if we look down below, if we were to draw both of them in the same graph, then we'd have our function f of t, so we should now call her f of tau. And we have this other function here, u of t minus tau. Now you can see here that whenever this function here moves over onto the top of this function, we're going to have the product here, f of tau times u of t minus tau. Now we can see here that for the moment that's going to equal 0 for all values of t less than tau. So as long as this value t here is less than this value tau here, then this little wave here, the unit step, has not crossed over and impinged on this f of t. Okay. Now we can see then that this here is going to equal, well, whenever it runs over the top of it, it's going to be the f of tau times u of t minus tau. Now the u of t minus tau is always of a height 1, but f of tau, well, that can be any particular function, so it would just be 1 times this particular function f of tau. So this value would just give us a value of f of tau for all t greater than or equal to tau. So let's continue with this and we'll see how it gives us integration. So let's now imagine that we've taken our function f of tau and we've shifted over our step function over the top of it, and we've formed this product f of tau u of t minus tau. But we can see here that if we were to integrate this from minus infinity to infinity, what we would do is we would take in these little area elements. So for example, if we look at the graph below, when there's no overlap, there's nothing here, but as soon as there's an overlap, there's a height. Now that height there would be the area of this little element, and as it moves to the right, you'll see that the height here, in this case, this is just a standard function which has got a height of 1. So the height here is just going to change linearly, because the area is going to change linearly as this u of t passes over the top of it. So we're going to get this effect here as just a linear increase. Now you can see here that this here is the integral of this function here. Equivalently, you could look back the way, you could say this function here is the derivative of this function here, because if you look at that there, it's just a constant rate of change, so the height here would just be a constant. Now the problem I have with this here is that this function here, u of t, it goes off to infinity in the negative direction, so as it passes over, there's always going to be an area of overlap because it just goes on forever. So that would mean that this point here would just continue up and up forever. Now we don't want it to do that. We want it to stop at a certain point. So they want to stop at a point here, which is the end of this little function, which is a point t. So we really just want to integrate it from minus infinity to our point t of the function f of t times u of t minus tau by d tau. Now if we do that, then we're able to say that the integral from minus infinity to t of f of t by dt is our f of t convolved with u of t. So that's a little argument, a heuristic argument, that if we convolve a function with the unit step, it's equivalent to integrating the function. So if we take our function of time and we convolve it with the unit step, then we get our integration. Now we already know, because we've seen it in the previous video, that if you were to convolve two functions in the time domain, it's equivalent to multiplying them in the frequency domain. So it means that our functions f of t convolved with u of t in the frequency domain is equivalent to our f of I omega times u of I omega. So we call this other function g of I omega, and that's our u of I omega times our f of I omega. Now we already know what this u of I omega is. This is just the Fourier transform of the step function, and we've already worked that out in a previous video, and that's equivalent to 1 upon I omega plus pi delta omega. So we're taking that 1 upon I omega pi delta omega and we're multiplying it by our f of I omega. So finally the Fourier transform of a integral is going to equal 1 upon I omega f of I omega plus pi delta omega. Now this last term here, f of I omega, well, delta omega f of I omega, well, the delta function is only defined at point 0, okay? So if we multiply that by a function, then really from the shifting property, the delta omega f of I omega is the same as the delta omega f of 0. So that's the shifting property there. We've seen delta t f of t would just be a value f of 0. So the Fourier transform pair we're looking for is the integral from minus infinity to t of f of t by dt is equal to 1 upon I omega f of I omega plus pi delta omega f of 0. So let's look at this now in Matlab. So this is the output from Matlab. It's showing you a function f of t being convolved with the unit step u of t, and it's producing the integral of the function f of t. So let's have a look at it live in Matlab. So let's look at this example here. We've got a little square function, and when we find the Fourier transform of that function, we get this sinc function, and you can see it's a purely even real function. There's no imaginary part to this. So just as a reminder down here, what we want to do is we want to integrate this function, and then we want to look and see what happens to the frequency domain equivalent of the integrated function. Now we've seen from our analysis that it should give us 1 upon I omega times our function plus this term here. So really we're going to end up with two parts whenever we do the integration. We're going to end up with this part here. So this division by I is the same as multiplication by minus I. So that'd be equivalent to rotating the entire function onto the imaginary axis. So we just multiply by I, moves at 90 degrees, so we just rotate it onto the imaginary axis. And then we also divide by the value of omega. So that's one thing that we're going to see. Now the other thing we're going to see is an impulse function. So let's go ahead and we'll have a wee look and see the actual output. So this is the output generated from Matlab. This is the integration of our function, and this is the function that we get out in the frequency domain. So this is the Laplace transform of the Fourier transform of the integrated function, and you can see it's a complex function. It's got real and imaginary parts to it. But let's have a wee look at this actual in Matlab, and we can move this function round about, and you'll see the two parts of this function, which is the delta, pi delta omega, and the f of I omega divided by I omega. So let's look at that now. So again, we're going to use this file f1.m, and we're going to take our original function, which is an even square function, and we'll find the Fourier transform of it. And we can see that, as we've seen in the previous slides, that's our function there of time, and it's an even function, so the Fourier transform gives us this sinc function, which is an even function and it's purely real. So we've seen that in the previous video, the previous slides. So we're going to go now and we'll integrate this here, and we'll look and see what happens to the function in the frequency domain. So in order to integrate it, first of all, we've got to tell it out the function is actually a function of time there. So we'll put this little section in, and then we'll go ahead now and we'll differentiate that function. Sorry, we'll integrate that function. So we're going to integrate the function here, a little square function there, and we get this new function here. So we'll take this new function here and we'll find the Fourier transform of this new integrated function. So that's our little command there. So it's f1, and this is the new integrated function. Again, all of these functions are available in the resources section in the text file. So whenever we look at that, as we've seen in the previous slide, we get the integrated function here. Now we're looking to find the Fourier transform of that integrated function. You can see here we've got our frequency domain and we've got an imaginary axis and a real axis, so it is a complex function. So we'll look at first of all the real section. So the real section here, it would tend towards a sinc, the sinc function would tend towards an impulse function. So this here would be our pi delta omega section of our integration. So now if we look at the imaginary part, you can see the imaginary part here, and what's happened is that the function here has been divided by I, or if you like multiplied by minus I, so that's shifted it 90 degrees, so it's shifted it onto the imaginary plane. And of course we're dividing by omega as well, so division by omega actually changes the shape of this function. So that's as we expected to see from the previous slide. So one more thing to note here is that this value here, f of 0, gives us our constant of integration, or if you like in electrical engineering terms, our DC value. So that's all there is for this video. I'll get you on the next video. Goodbye.